Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on graphing trigonometric functions. Now, this is actually the fifth day in our chapter for trigonometry, and I'm actually not going to graph the trigonometric functions, but I'm going to help you identify all the parts you need to know, so therefore, if you need to graph them, you can. So part of the parts that we're going to figure out is we're going to identify what the graphs look like, so we can see these kind of parent graphs for sine, cosine, and tangent, and then we're going to learn how to basically identify the parts. So for sine and cosine, that's going to be amplitude, period, phase shift, vertical transformation, domain, and range. And then for tangent, it's basically just going to be the exact same, but we're going to add in the vertical asymptotes, as well as there is no amplitude for that. So we'll get to that once we get to the vocabulary part of the lesson. But before we do that, I wanted the students to investigate and kind of see where these graphs come from. How do we create these graphs? So therefore, they know that they can recreate them really at any time without having to like memorize the graphs, which sometimes people get them confused. So it's important to understand where these graphs come from. So what I did is I gave the students a whole bunch of angles. All these angles actually are from the unit circle. And I basically gave them out some cards and said, let's evaluate for the sine, the cosine, and the tangent of all of these angles. Now, I didn't ask every student to do each and every one, but I gave them, a couple of each one, and then we went ahead and plotted them. Now, obviously, when you plug in like the sine of pi over 6, that gives you 1/2. So therefore, you could plot that on an XY axis. However, the sine of pi over 3 is going to be square root of 3 over 2. So I just gave them the decimal equivalent, 0.86. So therefore, they could draw this on an XY axis. So, basically, when we're evaluating the trigonometric functions, remember, we can evaluate those for those angles based on points on the unit circle. So therefore, the sine of theta was y, the cosine of theta was x, and the tangent of theta is y over x. So that is for each one of those trig functions of an angle represents those coordinates on the unit circle. But then what we kind of did, and it's kind of tricky, is then what we did is we took those coordinate points and we plotted them on an XY axis. So here is an example of what sine looks like. Now, if you have y equals sine of theta, now again, that's kind of the same thing as y equals like sine of x, right? I mean, but I don't want to confuse you with the x and y being the x and y from the unit circle to being the x and y here, because the x is the same thing as the theta. It's the angle, right? So that's the input of these functions, because remember, trigonometric functions are functions. You have the input and you have the output. So in this example, sine of theta, this is going to be our theta axis. And you can see our theta axis, which is also known as the x-axis, is represented by angles, all right? Now, these angles, for each one of these angles, as I mentioned, you can find a point on the unit circle, and that's how we found the output value. So, for sine, the output value is the y-coordinate of each of the points on the unit circle relative to the angles. So, for instance, let me just do kind of one here. For instance, sine of pi over 6. Well, here's pi over 6. So if I, for instance, I gave students like sine of pi over 6. So that coordinate point for pi over 6, that coordinate point is going to be square root of 3 over 2, comma 1/2. Okay, so if I wanted to plot this point, pi over 6 is going to be my input variable. So basically what we're doing is we're graphing a input variable and a output variable. So theta is my input variable, which is pi over 6. And then my output is, what is the sine of pi over 6? Well, remember, when we have a point on the unit circle, the sine represents the y-coordinate. So my output value ended up being 1/2. And that's how I plotted that point. And if you plot all of these points, you can kind of see we have a general shape. Now, just to note, my scale is not really proper because, some of these points are going to be a lot closer to each other than others. This is not actually evenly distributed like this. But I just wanted to kind of give, this is the only scaling that I could create, so I just wanted to have something. But, excuse me, if we go ahead and connect these, you can kind of see we have this nice little curve. And this is one thing that we kind of talked about in the class is like the shape, right? So this represents going all the way around the circle, right? This represents finding all these angles around the circle. These are all those output values. So there's a couple things that should make sense. One, it has a maximum point of 1 and a minimum point of -1, which makes sense, right? Because if you're looking at all the x and y coordinates, right? or actually sine is just y coordinates. So if you're looking at all the sine coordinates, the farthest the y coordinate is, right, away from the origin is 1, right, which is like right up there, 0, 1. It doesn't get any larger or farther away than 1. And again, that makes sense because the unit circle has a radius of 1, right? So that's why we have this max and min is 1. But we recognize, though, we can also go around the unit circle again. Like this is just one revolution. After we do one revolution, we're going to start hitting the same values again. So a couple important points is, one, this graph is going to continue in that direction and in that direction. So it starts repeating itself. Now, what we call this, how long it takes for the graph to repeat itself is 2 pi, which is basically one revolution. In addition, we could also start looking at some kind of symmetry. So it's a little bit easier to look at once you start zooming out from this graph. But obviously, if you take this graph and flip it over, you can see that it's not symmetrical about the y-axis. But actually, this graph, if you reflect this about the x and then the y-axis, it makes sense that there's going to be a point down there at negative pi halves, negative 1, because you can kind of see that. And we'll look at the graph, and you'll be able to kind of visualize that a little bit easier. But for right now, we recognize that this does have symmetry about the origin, so therefore sine is odd. We see that there's a maximum point of 1 and a minimum point of negative 1. So it's also bounded. This is an absolute maximum and this is an absolute minimum. We can also see that the increasing, decreasing intervals keep on changing. We're not going to spend too much time really on that, but that is something just kind of important to remember. And then also we see that the graph kind of continues, right? And there's no discontinuities, right? There's no reason for any angle for us to have an undefined value, right? We've already talked about undefined values so far in this class as far as dividing by 0 and taking the square root of a negative number. Well, when you're just looking at the y coordinates of points on the unit circle, you're never going to be dividing by 0 for sine, right? So therefore, we're going to be defined for all angles, meaning that the domain of this graph is going to be all real numbers. So then we did the same thing for cosine. Now, again, really the only difference is cosine just represented the x coordinates, right? And we can see that the graph looks very similar to the sine. So, now this is the x coordinate, or y equals cosine of theta. So again, we have our theta axis and our y axis. And again, my graph is not supposed to be perfect, but hopefully you guys can kind of see the general idea of what it looks like. And when we put these, together next to each other, when we put these, angles onto it, it looks like they're just kind of a shift over, all right? But again, same thing, like we're going around the unit circle. This is just going around the unit circle once, again, representing the x coordinates. But what's important about this, though, as well, is if we, continue this graph, you can see it's going to kind of take that shape, which looks like it actually has symmetry about the y-axis, which in that case means that the function is going to be even. So that's something, again, important. We'll talk more about that later. But you can kind of see that if you continue the pattern, it looks like it's going to be symmetrical about the y-axis. Same kind of thing. There's a maximum point of 1 and a minimum point of negative 1, which again, like if you look at the unit circle, those come on, move that. There we go. If you look at like the unit circle, the points on the unit circle, the farthest x coordinate is going to be 1, right? It doesn't get any farther away than 1 on the unit circle. So that's why we have that maximum and that minimum point. And again, like it's equal to 1 at 0 and it's equal to negative 1 at pi, right? And a lot of times people did make some wrong points, and I'll kind of explain how it's really easy to determine. Sometimes, I had a student that was, the point was like right here, or they had a point, up here. And so one of the things that we could check our work with, and again, this is one of the things that, again, is making that relationship that I want students to understand with the sine and the cosine graphs based on where they come from. So where they come from, or again, what you look at is like, let's look in this first coordinate. In this first quadrant, right, for all the angles in the first quadrant, which is basically angle 0 to pi halves, all the x coordinates are positive, right? And you can see the graph is represented by all positive values. However, once we go from pi halves to pi, right, all the angles pi halves to pi, you can see the x coordinates are all negative. And look at these y coordinates here are all negative. Then we go from pi to 3 pi halves. Again, the x coordinates are negative, and you can see how these output values here are negative. And then once we get from 3 pi halves to 2 pi, you can see the output values are going to be, again, positive. I know it sometimes gets confusing using x and y's kind of like interchangeably for both of them. So that's why I'm trying to use like input, output. Like input is theta, output is this y coordinate of the graph, not to be confused with the y coordinate on the unit circle, right? And you can see how that plays out as well with the sine. From 0 to pi, right, sine is always positive. And then from, pi to 2 pi, you can see how the y coordinates of the unit circle are all negative, right? And that's why those produce those output values to be negative. The other thing, just a real quick, I forgot to mention, you can see that I didn't write down these coordinate points. Square root of 3 over 2 is 0.86. Square root of 2 over 2 is 0.70. So that you can see those are the tick marks represented right there. And I didn't do that for tangent as well, did I? My bad. So let's see. There was the square root of 3 over 3. And then there's a square root of 3. And I forgot to mention that. I forgot to put that in there. So the square root of 3 is 1.73. And the square root of 3 divided by 3, come on. What? Square root of 3, and then divide that by 3. Yeah, 0.57. Okay, that was 0.57. So you can see that's where those tick marks kind of came in, just so you can kind of see. So here we went ahead and did the tangent graph. So they did the same thing. Now, students, a lot of times they had trouble. Typically, students had trouble, and this one was obviously with pi halves and 3 pi halves. So we have to kind of understand, again, what are we doing with pi halves and 3 pi halves? So tangent of x, or we could look at that at tangent of theta. Okay, so again, I think it's really important, again, if you understand the unit circle here, what is going on? Right? So at pi halves, this coordinate point here is 0, 1. That means the tangent y over x. It's undefined, right? And so it's like, well, what do I graph when it's undefined? And the best answer is nothing, right? It's undefined. You don't put anything there. However, in graphing, if you were to graph this graphing calculator is not going to put anything. Desmos online doesn't put anything there. However, we do want to represent like what exactly is going on. Like it is a discontinuity. Is it a hole? Is it removable? Is it an asymptote? Is it non-removable? And in this case, we can see that it doesn't really look like it's anything going to be removable. So we're going to represent it as an asymptote. And therefore we can just show that it's a dotted line, just so we know that not only is it a discontinuity, like it's undefined, but we can see that this graph is going to be approaching the asymptote, right? And that's the important thing about understanding it's an asymptote, is that this function is going to be approaching the asymptote. And that's the same thing for 3 pi halves. Over here, that coordinate point is 0, 1, right? So you can see that the, again, -1 over 0 is undefined. Now, again, students made the same kind of mistakes. They made positive points when they should have been negative. But again, if we understand that tangent is positive in the first quadrant, negative in the second, positive in the third, and negative in the fourth, we can double check our answers. Besides that, the other one was just doing the ratios, which again, we're going to get, more familiar with evaluating for all these angles. But again, here, when the angle is in the first quadrant, all my output should be positive. From the second quadrant, pi halves, to pi, my output value should be negative. From pi to 3 pi halves, which is the third quadrant, my output values are positive. And then from 3 pi halves to 2 pi, you can see my output values are again negative. Now, I want to kind of, again, as I mentioned, guys, my scaling is not ideal here, right? So I'm trying to just do my best to kind of show you guys, but it looks like this kind of S curve that's going on. And again, the scaling is way off, guys. These are not evenly distributed scaling. So besides overlooking that part, there's something that's important that's going on, because tangent looks absolutely nothing like sine and cosine. Sine and cosine, right, kind of have this nice little ups and downs, little ebb and flows. There's no discontinuities. We can see that after we've traveled 2 pi, the graph starts repeating itself again, right? Because that's going around the unit circle. And it's nice, it's just like this nice little wave here. Whereas the tangent, we obviously have undefined values, because again, that makes sense. It's the ratio of y over x, and x can be 0, especially at pi halves and 3 pi halves here. It looks like it's always increasing. It's not changing from increasing to decreasing. And it looks like it does repeat itself. It's kind of odd to kind of see this repetition here. But if you kind of look at it, like that looks like the other part right there. Like if I were to expand this out, like if I was to keep on going around the unit circle, it looks like the next thing I would do would be continuing this graph like over here. So it does look like it repeats. Then we need to kind of understand, well, how long does it take to repeat? Is it 2 pi or is it shorter? And it looks like, really you're just getting this little S curve. So what is the length of the S curve? And you could say, well, from pi halves to pi, like how far is it from here to here? Well, hopefully you can see that pi halves plus pi, right? Or 2 pi over 2 gives you 3 pi halves. Another way you can confirm that is it looks like the asymptotes are occurring every pi. Like here's pi halves. You add half of a circle, which is pi. Then you add half a circle again, which is pi. Half a circle, which is pi. And you can keep on adding pi. Now, that brings up to our next point is, well, then how can we identify all these asymptotes here, right? Because it looks like there's a lot of asymptotes going on. And I don't really want to write down all the asymptotes, but let's try to maybe make sense of them. So we know that the first asymptote occurs at pi halves, and then the next one occurs at 3 pi halves. And then if you add, again, pi, you'd have 5 pi halves, 7 pi halves, 9 pi halves. And then you realize, wow, I can keep on adding repeatedly, like keep on adding pi continuously. So how can I represent repeated addition? And that the answer is multiplication, right? Well, how many times, what am I going to multiply by? Like how many times could I, keep on adding pi? And we don't know, right? It's an unknown. You can do infinite many times. You can go around there infinite many times. So to represent an unknown that can go all the way up to infinity, we can multiply pi by the variable n. And n just basically represents the number of times you can add n or subtract n, right? Because n can be negative. And again, let's kind of make this case. Let's say n is 0. That means there's a vertical asymptote at pi halves plus 0, which is pi halves. Got it. What if n is 1? Well, if n is 1, that's going to be pi halves plus pi, which is 3 pi halves, right? And then what if n is 2? Well, that'd be, again, going to give us 5 pi halves, which kind of makes sense. That's the next asymptote. What about if n was negative 1? Well, that'd be pi halves plus negative pi, which ends up giving us negative pi halves, which looks like based on this symmetry is going to work. And the symmetry might not be obvious in this case as well. So what we're going to do is we're going to look at this graph in a little bit different direction. And that's what we call with our parent functions using the initial period. So, the whole purpose of me doing this, probably took like 30 minutes of my class to kind of go through this, is because I really wanted students to understand where the graph came up. But if students really want to graph it, I'm not going to expect them to plot all those points. Like it's kind of crazy. However, I think if any time a student is confused or kind of forgetting about what the graph looks like, they can always remember this portion of the unit circle. And then from here, they can represent the initial period of a trigonometric function. Again, these are the trigonometric functions, just looking at the first revolution, right, from 0 to 2 pi, except for the tangent one. And just using these 4 points, these 4 angles, 0, pi halves, pi, and 3 pi halves, and 2 pi, I'm sorry, so I guess 5 angles. But using those angles, you can easily plot those points and then just make the connections, understand where the max and the mins are and where the x-intercepts are. And again, you can just see like, the y, this represents all the y coordinates for each angle, like 0, 0, pi halves, 1, pi, 0, 3 pi halves, negative 1, 2 pi, 0. This one represents the x coordinates of these points at 0, 1, at pi halves, 0. So you can kind of see how that relates. Now, tangent doesn't really seem like, that last graph was kind of confusing. So what we do for tangent is we still want to get like an actual full S curve between two asymptotes. But rather than doing between pi halves and 3 pi halves, if we actually look at between negative pi halves and 0 and pi halves, we still get that nice full asymptote, right? And instead of doing a revolution of the unit circle, it's really just half revolution positive and then half the revolution negative here. It still gives you a full period, but I think it's a little bit nicer. You can just kind of see how that full version of it is. And from there, you can also see that we already confirmed that negative pi half was an asymptote. But also in this case, what we can see though, is that the graph is odd. It's symmetrical about the origin, like reflect about the x-axis, reflect about the y-axis, you're going to get the exact same graph. So, but just remember, these are just the initial period, right? These graphs continue indefinitely in both directions, positive and negative, because again, they come from the values of the unit circle, right? So you can keep on going around the unit circle in the positive or in the negative direction. All right, but now what we want to do is, now as we get into the graphing portion, what I want to do is just remind students is like, what do we already know? We already know transformations of functions. That's something that we've already covered in this class. So, if I give you a trigonometric function, it doesn't matter if it's sine, cosine, tangent, Or if it's not a trigonometric function, if it's x squared, x cubed, square root of x, cube root of x, e to the x, ln of x, like 1 over x, it doesn't matter the function. If you're multiplying on the outside by 2, that is going to be stretching the graph vertically. If you're multiplying by a factor between 0 and 1, that's going to be vertically compressing the graph. If you are multiplying by negative on the outside of the function, that's going to reflect about the x-axis. If you're adding 1 outside the function, that's going to shift it up. And if you're subtracting 1, that's going to be shifting the graph down. Notice that all of those transformations are all outside and they all impact the graph vertically. So again, just to kind of reiterate, make sure we're really good with this. Let's go and just take a look at Desmos just to kind of verify all of this stuff. Okay, so on to Desmos. What I did is I plot a lot of this stuff in here. So in this case, I have sine of x. And you can see, like, we only talked about the initial period, right? Between 0 and 2 pi, which would be like 6.28. That was our initial period. But obviously, you can see that this graph, how it like expands out as you zoom out, right? So it keeps on going on forever, just continuing that same pattern. All right. So a couple things again. Let's go through this. Multiplying by 2, that is going to be vertically stretching the graph, right? See how it vertically stretches it. Here we have this horizontal compression. Okay, when we multiply by a negative, that's going to reflect about the y-axis. Okay, adding 1, that's shifting the graph up 1. See how everything moves up 1, everything moves down 1. So again, notice how everything that I just did is a vertical shift upward, or is a vertical transformation, right? Then the next slide, we talked about these cosine ones. So I went over and gave them the cosine graphs. And just to kind of save some time, we'll just look at cosine. So here's the cosine graph. Again, now we can put them in because my class got to see this. But you can see, here's the sine and the cosine graph. You can see that they're very similar to each other, right? It's basically the exact same graph, just kind of shifted over. And that's something we'll talk about really in next chapter as far as understanding a little bit more of that relationship. But but let's go and focus on cosine here. So now we're looking at the operations, inside the function. So we know multiplying by 2 outside, we're vertically stretching it. So if we multiply by 2 on the inside, that's going to have the same operation, but it's going to be horizontal. So how can we like stretch it vertically, but horizontally? Well, that's going to be a horizontal compression, and let's kind of see. Yeah, right? Now again, something's interesting. The distance it took for the graph to repeat itself just got shrunk, right? Instead of it being from here to here, now it's from here to here. So this horizontal compression changed how fast the graph repeated itself, which is something we'll talk about. Then you can see here, when we divide by 2 or multiply by 1/2, you can see that there's horizontally stretching the graph, right? Kind of like a vertical compression. Not the same, but it's the same kind of, same kind of idea. It's being horizontally stretched. You can see that also, that changes again how long it takes the graph to repeat itself. All right. Obviously, we have the negative reflection, and I was kind of like, having fun with students, making some jokes. But you can notice that this graph is symmetrical about the y-axis. So if you flip this graph around the y-axis, you're not going to notice anything, right? Because it's an even function. However, though, just note that that is a reflection about the y-axis. And then obviously, if we're adding something inside of the function, remember that shifts it to the left, right? And we're going to verify this again. And if we are adding an angle, that's going to be shifting it to the right. So you can see how that graph is actually being shifted to the right. All right. And then the last one I wanted to show, the last slide that we talked about, was the tangent. So let's go and look at the tangent function, which again, you remember, it doesn't show the asymptotes, right? But you could draw the asymptotes if you wanted to, like kind of draw the lines where they would be. But again, this repeats indefinitely. Okay. And you can see how that's why like from 0 to 2 pi was like this portion, and then half of that. It's kind of weird. So you can see how this is like this nice little initial period between negative pi halves and pi halves right there. In this one, we want to look at the combinations, right? So my point that I'm trying to bring up is like when I have negative tan of x minus 1, does that mean I shift the graph up 1 and then reflect it? Or should I reflect the graph and then shift it down 1? I'm sorry. Should that mean I shift it down 1, so it's down 1, and then reflect it, so therefore it's going to be up? Or should I reflect it first and then down 1? So again, when you're looking at a combination with a reflection and a vertical shift, follow the order of operations. If I wanted to evaluate the tangent of pi over 4, let's say. So at tangent of pi over 4, I'm going to evaluate tangent of pi over 4, which is 1. Then I'm going to multiply by negative 1, which is negative 1. Then I'm going to subtract 1. So again, you're following the order of operations. You're going to multiply by -1, which is the reflection first, then you're going to subtract the 1, which ends up giving me a -2. So therefore, when you see at pi over 4, which would be somewhere over here, you can see that that's going to be equal -7.8, which if you remember on my point is -2. So they don't do it in radians, but you can see how that makes sense. So the graph is not up there. You don't shift it down and then reflect it back up. You reflect first and then move it down. The other one comes into, a lot of people remember, oh yeah, +1/2. So therefore it's, left pi halves. And then they say, well, this one's left pi halves. But again, be careful. You have to factor out the 1/2. This is, I'll show you actually in this. This is actually going to be pi to the left. And we'll look at this. But you can see it's not pi halves to the left. It's actually pi. So you can see -pi halves to the left. All right. This one again, and again, I'll show you in the slides, you can see this. In this case, you have a reflection about the y-axis because that's a -x, and you're actually shifting this pi to the 4th to the right. So this is actually a transformation to the right, not the left. So you can see how the graph got shifted to the right, and it's reflected because that's a -x. And then this one that's actually going to be pi halves to the right. And again, guys, I'll show my work, but you can see how this graph actually got shifts pi halves to the right. Yeah, pi halves to the right, which actually, and then also there's a period change. So kind of look a little confusing, but the main thing is I want you to see it's not the same graph just being shifted, pi over to the right. And I'll show you what we need to do again with that once we get back into the slides. So let's go and take a look at the slides because I think looking at the algebra for this is a little bit easier to be able to understand everything. Okay, so in this case, we're just going to investigate sine, although we could be using any one of them. So again, remember D, when a D is positive, that shifts the graph up. When D is negative, that shifts the graph down. Fairly basic one. Most students kind of remember that. Again, C though is one of them ones that students, a lot of times they still confuse. They don't understand why is it positive to the left and negative to the right. Well, again, notice as C gets positive, it's going to the right. Agreed? Stop. C is 2.5. It's moving 2.5 to the right. Again, if you were to replace C with 2.5, the equation would be bx minus 2.5. So you can see how this equation, it looks like it's negative, but again, it's a positive C, so you're shifting it to the right. And as C gets more and more negative, you can see we're moving to the left. Where C is negative, we're moving to the left, and then stop, C is -1. Now, if I were to replace C with a -1, it'd be minus a -1, which we'd represent as +1, right? Minus a -1, +1. But you can see, again, it's shifting it to the left. All right, now let's go ahead and take a look at the A. Keep on forgetting to switch those around. So again, A, remember, is that vertical stretch or compression. So when A is larger than 1, you can see how it's vertical stretching the graph. Now, it's very important for us to see this, that we're vertically stretching the graph, right? But again, notice that the x-intercepts, the zeros of the function are not changing, right? And if you remember, that was something really important that we talked about in polynomials. Like when we have scalars, that stretch or compression, that does not change the zeros, right? It just is a stretch of the graph. And then obviously when we get between 0 and 1, you can see how that's horizontally stretching the graph, but again, or vertically compressing the graph. But again, that vertical compression is not changing the zeros. And then obviously we get to 0, where A cannot be 0 because then we just have a line. But as we get to negative, you can see now it performs kind of the same way. Now there's something important that's happening here. When A is -2, look how low the graph goes, -2, and how high it goes, right? Which makes sense. We'll talk about that in another problem. But you can see when it's -2, the max to the min is -2 to 2. Yet when it's +2, again, it's the same thing from -2 to +2. So, either way, no matter what's happening, you can see how this stretch and compression is just really kind of changing with those graphs, but the x-intercepts are, again, remain the same. These are your scalars. But again, really notice that A really tells us how high and low the graph goes, and it doesn't matter if it's positive or if it's negative. I was trying to get to 0. But we don't want 0. We want 1, actually. All right, so then let's go and look at the 1. Okay, so when we're looking at 1, I need 1. Okay, when we're looking at B here, remember if b is going to be inside your function, right? So when b is larger than 1, what's that doing? And that's compressing the graph, right? See that the distance it takes the graph to repeat itself, see how that's being compressed, right? And then when b is less than 1, you can see how that's a stretch. Now, either way, if I'm compressing or stretching, notice how the distance it takes the graph to repeat itself is changing, as well as the zeros, the x-intercepts is changing, okay? And then obviously you can see how that really just kind of reflects. Obviously when b is negative, you can see how the graph reflects about the y-axis, right? That wasn't as apparent with cosine, but you can see how we have that reflection that's going on. As it's stretching, obviously when b is 0, you're getting a line, but you can see how that kind of works from there. And let's try to get to 1. Oh, almost. Okay. So that is basically it. Now let's kind of get into a little bit more of our formal definitions here before we actually get into some examples. Okay, so back to the notes. Let's talk about the parts of sine and cosine. So that distance, basically that max and min is basically kind of referred to as the amplitude. Really, the definition of amplitude is going to be the half distance from the max to the min. But if, as we mentioned, like when we see a 2 or a -2, that kind of tells us how high and low the graph goes, right? It goes, if -2 is in front, it went down to -2, up to +2. When +2 was in front, it went down to -2 and +2. Now, that's not always the same, and I'll explain a little bit more why that is the case. But it's just kind of important for us to understand from right now how that impacts the graph. It's the vertical stretch in both directions, really. So that's kind of the idea of the amplitude. It's the half distance from the max to the min. The period is actually the distance it takes the graph to repeat itself. So when we have these outside operations, that was not impacting the period, but only the inside ones. So you can see that's why it's 2 pi divided by the absolute value of b. The phase shift is basically the horizontal shift, how we're shifting left and right. The vertical transformation is basically the vertical shift, how you're shifting up and down. We know the domain is all real numbers. And then the range, I have this formula. I tell students, you guys can memorize the range if the formula if you want to. But again, look at the range here. For sine and cosine, it's -1 to 1, right? Well, if I shift the graph up 1, then the range, now the lowest point, instead of the lowest point being -1, the lowest point is going to be 0, right? Instead of the highest point being 1, the highest point is going to be 2. So therefore, the range is basically whatever the amplitude, kind of like that idea, plus, so it's like A, -A, +A, and then either, adding for your shift up or you're going down for a shift down. So once we get into these examples, I think it'll make a little more sense. But again, also remember period is, 2 pi. That's how long it takes the graph to repeat itself because that's a revolution around the circle. And obviously B is going to be horizontally compressing that or horizontally stretching that. So now let's go and take a look at the parts of tangent. So tangent is really, very similar as far as the transformations. However, the period is not going to be 2 pi divided by b. It's just pi divided by b because it only takes tangent pi to go ahead and start repeating itself. So the definition for the period for tangent is just going to be pi divided by absolute value b. The phase shift is c, and the vertical shift is going to be d. Now, we already talked about the vertical asymptotes. That's going to be pi halves plus pi n. The range, this one's kind of nice, that the range is from -infinity to infinity. That's why there's no amplitude here. Because again, if you look at the definition of amplitude, it's the half distance from the max to the min, right? Well, there is no max and min for tangent, right? It goes down and it goes up. So in this example, there is no amplitude. And as far as identifying the domain, this notation, which we haven't really used in my class, we basically just have done interval notation. This notation basically says all real numbers such that x cannot equal pi halves plus pi n. And again, that pi halves plus pi n is where the vertical asymptotes occur. All right. So those are kind of our 2 points here for the parts of sine and cosine and the tangent. And now we're just going to kind of get into some examples here. As I'm kind of working through these examples, if you want to go ahead and check, look at the graph version, then you can always use that link. But otherwise, I'm just going to kind of knock out through these examples that we kind of covered. And then so you guys can kind of see the steps that we're going to do. But if you want to see the graph, because you need to actually graph them, for your class, or you want to know how to do that, you can kind of confirm the graph by using that link. All right, for the first example, we have y equals the sine of x plus pi plus 1. And again, the definitions that I'm using here is just going to be from our notes that we previously took, right? The sine and cosine here. Oh, a little fast. All right, so the amplitude, remember, is absolute value of a, which in this case is going to be 1. So you can see there's would be a 1 right there. So therefore, absolute value of 1 is just 1. that's the max min. The period, again, is how long it takes the graph to repeat itself. 2 pi divided by absolute value b. Notice b, again, is the coefficient of x there. So that is, again, also going to be a 1. Let's try to do that a little better. All right. Let's put a dot there for that one, too. And so therefore 2 pi divided by 1 is just 2 pi. So basically this graph has not really changed at all, right? I mean, it's not being stretched, vertically compressed, or not being horizontally stretched or compressed. Yet though, we do have a phase shift. The graph is being shifted pi to the left, as well as there's vertical transformation up 1. So using that information though, we can identify there's no change in the domain, right? It doesn't matter. The domain's always real numbers. So it doesn't matter what transformations happen. The domain's always going to be all real numbers. Yet the range though, is going to be from 0 to 2. And the reason why is kind of what I explained. Like if the amplitude is 1, that means the graph goes down to -1 to +1. And if the graph is being shifted up 1, now the graph is going to be from 0 to 2. So again, if you want to verify the graphs or take a look at it, I have the link provided for you. And that will help you understand a little bit more what the graph is. But for kind of the sake of time, I'm going to work through all these, just identifying the parts of each graph. All right, so let's go ahead and just work on the parts of sine. So again, the amplitude here is just going to be the absolute value of 3/2, which is just going to be 3/2. Now 3/2 is a fraction, but it's larger than 1, so it's technically vertically stretching the graph. That means but the graph is still going to go up to 3/2 and then down to 3/2. The period is going to be 2 pi divided by the absolute value of -4, which is 2 pi divided by 4, which equals pi/2, right? So again, you can see that the graph started at, you can see the graph started at pi, and then it got compressed to pi/2, right? So you can see that period, how it got compressed. That's why that 4 is a compression. That also means that's a negative. That's a reflection about the y-axis. So I'm going to want to write that in there as well. So reflect the y-axis. There is no shifting left or right or up or down. However, the range changes by the amplitude, right? And again, we looked at this on Desmos. Like when that a was 2, it went down to 2, up to 2. So if a is 3/2, that means my range is going to be from -3/2 to 3/2. So the domain is just the same, but my range is going to be from -3/2 to 3/2. All right, let's look at the next one, which I guess I don't know why I didn't do sine. That's kind of weird. I'm going to add one of these. Sine one of those? Yeah, let's do, let's change this to a -1. Okay, let's look at the next one. The next one here has a amplitude. Wait, let me just double check, sorry. Cosine, I did one of those. I wanted to do, did I do one for tangent? Please tell me I did this one for tangent. No, I didn't. Okay, I'm going to change this then. I'm going to do this one. There's a certain problem that I was looking for. Let's do this one, a -1. Okay, so in this case, again, we're just going to have a y equals, the amplitude is going to be the absolute value of -2. That was right. What am I doing? Which is just 2. The period in this case is going to be 2 pi divided by, now again, this one's kind of confusing because what's b, right? Is it a 1? Is it a 2? Or is it 1 divided by 2? Well, the answer is it's 1 divided by 2, right? Because x over 2 is equal to 1/2 x. So you can see dividing by 2 is the same thing as multiplying by 1/2. So now I'm just going to multiply by my reciprocal, and you can see my period is 4 pi. So instead of the period being at 2 pi, right, when you multiply by 1/2, it stretches the graph horizontally to 4 pi. There is no phase shift. There is no vertical transformation. Again, I am now reflecting the x-axis. Okay. So now I'm reflecting the x-axis, and then the domain is still the same. And the range, though, is now going to be from -2 to +2. All right, last one here. Again, I'm adding this shift. Actually, you know what? Let me change that to a black, just so I can remember this shift here. All right, so in this case, again, now we have a fraction, but it's less than 1/2, so it's actually going to be compressing the graph. That means the graph only goes down to 1/2, up to 1/2, right? So for my amplitude, that's just going to be the absolute value of 1/2, which is 1/2. My period in this case, my b is again 1, so that's just going to be 2 pi. 2 pi divided by 1 is just 2 pi. We do have a phase shift. We are shifting the graph pi halves to the right. All right, and we are shifting down 1. Now, as far as my domain, again, or that's my vertical transformation. So my domain is still the same, right? However, my range, now this one kind of gets a little tricky. Like students are like, all right, you're at negative 1/2 to positive 1/2, right? That's the amplitude, but then you're going down 1. So like, what would that be? So that's where that kind of formula that I provided can be helpful here. This negative, negative a plus d, positive a plus d. So basically what I can have here is I can take negative 1/2 minus 1, and then I can take positive 1/2 minus 1. And by simplifying that, you can see that that's going to be a negative 3/2, and then 1/2 minus 1 is going to be a negative 1/2. So that is going to be a range. So sometimes when you're dealing with fractions or numbers that are maybe not as easy to be able to apply the operate, to add and subtract, using that kind of understanding the formula sometimes is helpful. That's why I wanted to add in that problem. And again, did I forget to write in range? Domain and range, yeah. Oops. Okay. All right, now let's go and get into cosine. So in this cosine example, again, really the same thing, right? We're looking for the same parts. We know the graph is a little bit different. So if we actually had to graph these, we would just have to apply them to a different paragraph because their initial period is different. But as far as the characteristics, they're exactly the same as what we just did. So again, in this one, we see that the amplitude is negative 2. So the amplitude is just positive 2. We have our period is going to be 2 pi divided by 2, which is just pi. We have a vertical shift down 1. Because you're subtracting 1. The domain is negative infinity to infinity. And obviously we have a reflection about the x-axis again. Did I do that x-axis? Yeah, I did. Okay, and that's y-axis. And then again, so if our amplitude in this case is from negative 2 to positive 2, right? The negative doesn't matter. Like the negative is just reflecting. It's still from negative 2 to positive 2. But now the graph is being shifted down 1. So therefore, that's why it's from negative 3 to negative 1. And again, we're using those brackets to make sure that you understand that that is a... we're using the brackets to make sure that we understand that the points are included in the range. All right, let's go ahead and do these 3 problems. So again, in this one, the amplitude is just going to be 1, absolute value of 1. The period is just going to be 2 pi. 2 pi divided by b, again, same definition. Here we're going to have a phase shift of pi over 4 to the left. And we're going to have a vertical transformation of up 2. So again, our domain is all real numbers, just like for sine. But our range, again, the graph is going from negative 1 to 1, but it's being shifted up 2. So now the range is going to be from negative 1 up 2. That's going to be 1, 3. For next one, we have a negative 1/2. So my amplitude here, amplitude is going to equal the positive version of that, which is 1/2. My period, I have a nice little tricky one here. This one's kind of interesting. I have a negative or 3 over 2. So again, it's 2 pi. And again, is it like 3, 3? Is it 2? Is it 3/2? Well, it ends up being 3/2. So again, we need to multiply by the reciprocal. And when you multiply by the reciprocal, you're going to get 4 pi over 3. So that's how long it takes the graph to repeat itself, which for graphing would not be that fun, but you could go ahead and do it. So there's the period. What else do I need to do? Oh, phase shift. There is no phase shift. There is no vertical transformation. We do have a reflection about the x-axis though. We have a domain, which is negative infinity to infinity. And we have a range, which is really just going to be from negative 1/2 to positive 1/2. The reflection does not impact that. All right, last but not least here is, again, just another example of the cosine here. So we have the amplitude is just going to be 1. The period is just going to be 2 pi. We have a phase shift of 2 pi to the right. And we have a vertical transformation of down 1. Okay, so again, the domain is negative infinity to infinity. And the range is going to be, was from -1 to 1, but now it's going to be from -2 to 0. And I put a parenthesis, which is wrong. You should use a bracket. Okay. All right, so that was it for sine and cosine. Basically kind of the same thing over and over again. I mean, there are more difficult problems I'm going to say I'm actually reserving for after we did this. But I wanted to kind of get these basic ones down for the sine, cosine, as well as tangent. Now, again, remember when we're doing tangent here, we're not identifying the... So we're doing tangent here. We're not identifying the amplitude. There is no amplitude. So if we have a number in front, that is like compression, right? It's a vertical either stretch or it's a vertical compression. In this case, we're multiplying by 1/3, so we can say that is a vertical compression of 1/3, right? The period, again, is pi divided by b. So in this case, we end up getting 2 pi. And again, you're multiplying by 1/2, so that's a horizontal stretch. The range is going to be all real numbers. And I'm not going to do, did I do domain? I did domain. You know what? Let's just scratch out domain. Because I told my students, you're not going to have to worry about the domain. And again, really, the domain is all real numbers except for where the asymptotes occur, right? So we don't really need to include that, again. The range, though, is going to be -infinity for all of them. And we'll just kind of get used to writing that. The hard part is the vertical asymptotes. And the reason why is the vertical asymptotes represent pi halves plus pi n. Now, again, if we have the tangent function, and this kind of comes important. Let's go back up to the tangent graph real quick. Do I have the tangent graph here? Yeah. All right, here's the tangent graph, right? The vertical asymptotes occur at pi halves plus pi n, right? Every pi away from each other. Now, if I stretch or compress that tangent function, the asymptotes don't change. If I shift the graph up or down, the asymptotes don't change. The only times the asymptote changes is when I'm shifting the graph left or right or stretching or compressing the graph. So what that means is anything inside of the function, right, is going to impact the asymptotes. So what I'm going to need to do when I need to identify my new asymptotes, I'm simply going to take whatever's inside my function. In this case, my function is x over 2, and I'm going to set that to the equation of the asymptotes. I then just solve for x, and that gives me my new equation for the asymptotes. So in this case, you can see x equals pi plus 2 pi n. All right, so let's just kind of work through them here. We have a reflection. X-axis, we're going right, pi halves, right? The period, that's the phase shift. The period is just going to be pi, right? Because b in this case is 1. However, the vertical asymptote, to do the vertical asymptote, you're going to take x minus pi halves. Why did I put a parenthesis there? So all you're going to do is do x minus pi halves equals pi halves plus pi n. So that's my original. Here it is with transformations. Therefore, add pi halves to both sides. X equals pi plus pi n. Now, if you have pi plus pi n, that is really going to be simplified to just pi n, right? Because it's just an extra pi. Okay, so we can look at the graphical portion of this. This is something we're going to dive into a little bit more deeper. But I just want kind of students to see this as far as when they're doing a multiple choice, how that would work. For this next one here, we have a 2/3. So even though it's a fraction, you can see it's less than 1 though. So therefore, that is a vertical compression of 2/3. We're multiplying by negative inside the function. So therefore, that is a reflection, the y-axis. We have this 2, so we know that's going to be horizontally compressing the graph, but we can just represent that with the period. So the period, again, is going to be pi divided by 2, not -2, because, again, remember, it's the absolute value. So pi divided by 2 is just pi halves. And then there is no phase shift and there is no vertical shift. So we're just going to leave it from there. And then the other thing is the vertical asymptotes. So again, we're just going to take -2, so the vertical asymptote. So we're just going to take inside the function and set it equal to pi halves plus pi n. So now we're just going to divide both sides by -2. So therefore, x equals, so negative pi halves divided by -2 is a negative. Pi halves divided by -2 is going to be a negative pi over 4. And then this is going to be a plus a negative, or just a minus, pi halves n. All right, and that would be your simplified version here. And again, you could subtract. You can just always leave that as a positive. You don't really need to subtract it because n is positive or negative. So therefore, we could just write that answer as a negative pi over 4 plus pi halves n. And really, that could also even be simplified to a positive pi over 4, really, because if you add pi halves to pi over 4, you get positive pi over 4. So why don't we just actually write that in there? And again, like I'm writing this so you guys can see, what a multiple choice answer would be. Those are equivalent, but typically we like to have the positive version. All right, last example here. We have I guess I just could have done a +1 there as well, right? Yeah, well. So in this case, we have a vertical stretch of 3. We have a period. Again, that's just going to be of pi. We have a phase shift, which is going to be left pi. And we have a vertical transformation, which is just up 2. Now again, it's like this is very important. Like if you originally had your asymptote at pi halves, but you move it pi to the left, like where is that new asymptote? Well, the interesting thing about this problem is it actually is just going to occur at back of that negative pi halves where we already had an asymptote. So let's kind of see how the asymptote here changes. I did forget to write the range, but I think you guys get the idea. All right, so vertical asymptote in this case is going to be x plus pi is equal to pi halves plus pi n. So if I subtract pi, I'm going to get x equals negative pi halves plus pi n, right? Well, again, what happens when you add pi to negative pi halves? You get, again, back positive pi halves. So this one actually is a transformation that's exactly pi, which is how long it takes the graph to repeat itself. So the asymptote equation is actually not the same. So again, this is, kind of a hard concept to like really understand, but the nice thing is next lesson, we do this a lot more in depth. So it's a little bit easier to pick it up on it. And also it's nice to kind of look at the graph so you can see how this works, which we'll kind of do more in the next lesson as well. But at least therefore you can see what the equations are. And again, I don't, for this first kind of quiz, I don't tell students they have to simplify it into the positive or the most simplified vertical asymptote equation. I just want to make sure that they can set whatever inside transformations equal to that equation for your vertical asymptotes, and then to go ahead and solve for x. All right, the last problems that we needed to do, guys, was just those combinations. Those ones that got so tricky for students is when you had the b and the c. And the main thing to do is remember when you have that b and c is to factor out the terms. You've got to make sure your x in this case is going to be 1. So therefore that represents your b, which in this case, in this problem was a -3, which therefore, since it's a -3, that means it's going to be a reflection about the y-axis, and it's going to be a horizontal compression of my period. Instead of my period being 2 pi, it's now 2 pi divided by 3. Our amplitude in this case is just absolute value of -1, which is 1. Since there's a negative on the outside, that's a reflection about the x-axis. We're shifting 2 pi to the right. Again, it's not 6 pi to the left. When you factor out the -3, you can see it's 2 pi to the right. My domain here is -infinity to infinity, and my range is still going to be -1 to +1. All right, so the last 3 problems we got here is just going to be these combined functions. All right, so in this case, we have an amplitude is equal to 3. Let's go ahead and first thing we need to do is factor them out. So in this case, I can factor out a 2. Factor out a 2, that's going to leave me with an x minus pi. Okay, so now I can say my amplitude is just going to be absolute value of 3, which is 3. My period, which is going to be absolute value of 3, which is 3. 2 pi divided by 2, which is pi. And then also I am going to have a phase shift, which is pi to the right. And there's no vertical shift, so I don't need to worry about that. I'm not going to be going up or down at all. But again, my domain here is going to be all real numbers. What did I say? Did I say just, yeah. Domain and range, and then my range though, let's see what the range is. So again, now my amplitude is 3, so it's going to go down to -3 up to +3, which is my amplitude. -3 to 3. Okay, so again, it's that really main important point is the factoring out the 2. In this case, we can see that the x is negative, so I'm actually going to want to rearrange everything. So -x plus pi halves. Then I'm going to want to factor out the negative. Okay. So we have the negative and we have the x minus pi halves. Okay, so amplitude, and there is no amplitude, right? Be careful. So you sometimes get like in those moods like, oh, amplitude, but again, there's no amplitude here. But we do have the period is just going to be pi divided by b. Well, b, remember, absolute value b. So since it's -1, we don't really need to worry about that. So that's just going to be pi. That does tell us, though, we have a reflection about the y-axis. And we are shifting right pi halves. Okay, there's no shift up or down, no vertical transformation. This does impact, though, our vertical shift, our asymptotes. So let's go and figure out our asymptotes here. So our asymptotes, I'm just going to take this equation here as it's originally stated. Pi halves minus x equals pi halves plus pi n. Right? Well, now, as I subtract pi halves, I get negative x equals pi n. And then if I just want to divide by -1, I get x equals negative pi n, which is really the same thing as x equals pi n, right? It doesn't matter if it's negative pi n or positive pi n. You're still going to have the same equation for the asymptote in that case. And that's basically it. And then at the end, guys, I'll show you guys one more actually trick we can understand here. But you can see that the graph does have a phase shift, which I didn't write, which is pi halves to the right. Oh, I did write that. So that's the phase shift, which is right pi halves. All right, and the last example here, we have an amplitude, which is absolute value of -4/3. So that's going to be positive 4/3. The range here is -infinity to infinity. I'm not going to do the domain because the domain is all real numbers except for pi n, right? The range, though, is -infinity to infinity. The amplitude here, it's a sine function. So the amplitude is 4/3. The period is, why do I doing that? Stop. We see, guys, before we even get to this, we see that I have a b. I got to factor out that b. So this one kind of gets a little difficult because how can you factor out a 3 from pi? 3 does not divide into pi, right? But again, really factoring out, guys, is the same thing as dividing out. So I can rewrite this as a -4/3 times sine of 3 times x plus pi thirds. And again, like double check my work. 3 times x is 3x. 3 times pi thirds is pi, right? So when you're factoring out, you really are dividing out. You're really dividing by 3. So the amplitude, again, is going to be an absolute value of -4/3, which is just 4/3. The period, in this case, is going to be 2 pi divided by 3, which is just 2 pi divided by 3. We are going to have a phase shift of pi thirds to the left. There's no vertical transformation. My domain is from -infinity to infinity. And my range is, again, going to be from -4/3 to +4/3. Now, how are you going to, let's say you're really struggling with this and you're like, I don't like factoring. I don't think I can do that on my own. Well, let me give you a little tip to end off this lesson as far as another way to identify the transformations. So the sine graph, the initial period starts at 0. So if we have any transformations, this initial period is going to move. So this starting point is going to move left or right. So if it moves to the one left, if I find the new starting point is going to be -1, that means I just had to move from 0 to -1, meaning the transformation was shifting left 1. So what we would do in the graphing form, if I actually was asking to graph this, what I teach my students to do is find the new starting point. So if you have a shift left or right, you're going to have a new starting point. So what you're going to do is set your transformations equal to 0. Then just solve for x, right? So originally, this is what we call the start. So originally you would start at 0, but now you're starting at -pi/3. So if you originally were at 0, but now you're starting at -pi/3, where did you go? Well, you shifted to the left, or for you, it's shifting to the left pi/3. That's why that is pi/3 to the left, right? It's not left pi, it's left pi/3 to the left. And that works for all of these. You can set each one of these equal to 0. And this one, you'd get x equals -pi halves, right? Again, that's shifting pi halves. Oops, I'm sorry, that's a positive pi halves. Right, negative divide by doing. So that'd be x equals positive pi halves. That means you're shifting pi halves to the right, which is obvious here, pi halves to the right. The only problem with using this technique is it doesn't remind you that there is a reflection there, right? This doesn't tell you that the period change or that b is 3. So it is helpful to identify the phase shift, but it's not really helpful in identifying the period and the reflections. And again, in this case, the same thing. Set 2x minus 2 pi equal to 0, and this x is equal to pi. So if we're originally starting at 0, but now we're starting at pi, that means we're shifting pi units to the right. So again, it's just another way for you to understand the transformations without having to factor, because I know sometimes taking a test or quiz, that can be confusing. So, all right, ladies and gentlemen, that is it. Feel free to add up any kind of reflection you have regarding today's lesson as far as understanding not only just the graphs, sine, cosine, and tangent, but also the components of the graphs and how to identify them from the equation. So I hope this lesson helps, and I look forward to seeing you guys on the next lesson. Cheers.